Now let's look at the same experiment we just did with paintballs, except now we're going to use light pulses. So this is diagram 3.1, the light pulse experiment. Again, Alice is moving in her spaceship. Bob is going to be observing. To start off, let's remind ourselves of one point that will be very key here. And forget about Bob for a minute. Let's just think about Alice. Alice is sitting in her spaceship. And as far as she's concerned, she's not moving. She doesn't see the clocks moving or anything like that. So when she sets off the light pulses here, one going in that direction with speed c, the other going in the other direction with speed c, it's just like our first diagram 2 video clips ago that we did, where she's stationary. She doesn't see anything special going on at all. She'll see one light pulse end up over here, one light pulse end up over here at exactly the same time. In other words, her perspective is that the light pulses reach each clock simultaneously at some time sub Alice, t sub a, equals capital T sub a. So when they hit, her clocks will read, at the beginning here, they read 0. Light pulses go off. She's just sitting there watching this. At the end, each of these clocks will read T sub a, and Alice will be saying, what's the big deal here? Clearly the photons, if we call them photons, I'm trying to call them light pulses because technically we don't have photons yet at this time of 1905, say. Einstein had introduced the idea of the light quantum number, but they weren't called photons yet. Minor point. So light pulses, photons, really whatever you want to call them. It's a light wave, a light beam, light pulse heading off in each direction. Alice just sees it, both of them arriving at exactly the same time according to her clocks. He says, no big deal there. Now we need to look, though, at what Bob is observing. Because remember, he's down here with his lattice of clocks. He sees Alice moving to the right at velocity v. Again, we will assume that when the light pulses get shot off, there's a little puff of smoke behind, as it were, right at that position. And Bob notes on his clock, takes a photo there, notes his clock is 0. All of them is 0 at that point. So he says, yes, I see that photons or light pulses were shot at time t sub b equals 0. And also for Alice, so we'll erase the capital T sub a here, because that's later on for Alice when they actually hit. But the important thing to remember is, as far as Alice is concerned, when these two photons hit, they both hit simultaneously, and the reading on her clock is capital T sub a. So keep that in mind here. So now that's diagram 3.1. Let's move on to diagram 3.2 and just move Alice over slightly here as she's going by. So diagram 3.2. A little room here. Okay, so now her ship is something like this. So let's see, it goes 1, 2, 3, 4. It's going to go to right here approximately. So there's her little narrower ship at this point. But she has one clock here and one clock there. And remember, this is Bob observing now. So this is where the photons are really in transit. But we have to think about a key thing here, and that is, with the paintballs, remember, the velocity is added. We had the velocity of Alice going in this direction, v, and now we have the velocity of the light pulses at velocity c. But remember, the principle of light constancy, Einstein's principle of light constancy, combined with the principle of relativity, led us to the conclusion that the speed of light is the same for all observers. Okay? If you have your light pulse gun here, and it's moving with velocity v, and you shoot a light pulse out, unlike a paintball, that light pulse will still be traveling here at velocity c. It will not be c plus v. It's just velocity c. And so let's think about this a minute now. So the clock here is moving away at velocity v. This light pulse is just traveling at velocity c. And the light pulse in the other direction is also traveling at velocity c. In fact, we'll just pretend by this point in time, it's reached this clock here and set it off. And look what Bob is observing. just because the fact that the velocity of light is always c and it's not c plus v, this light pulse, from Bob's perspective, will reach this clock after this light pulse reaches this clock, because this light pulse has been traveling at velocity c. Not c minus v, like in the paintball example, but just c. So this clock is moving away from this light pulse, and this light pulse is not getting any extra velocity to catch up to it faster. And this clock here is moving towards the leftward going light pulse, and this light pulse is not being slowed down at all, subtracting the velocity of the spaceship. So what Bob is going to observe, and let's just be clear here, so Bob's clocks no longer read 0. We're at some point, I didn't write zeros in all of them just to save a little time there. So now Bob's clocks at this point read, we'll call it time t b1. Okay, and these all read the same thing. Okay, so this is sometime later. Light pulses are in transit, but Bob notices that the leftward going light pulse hits this clock at time tb1, so it sees that. It says, okay, leftward going light pulse hits at time tb1. All my clocks are tb1, but he's still observing the rightward going light pulse. It hasn't reached that clock yet. In fact, it's not going to reach the clock until a little bit later. It will eventually catch up. Obviously, the speed of light is going to be faster than v here, v being less than the speed of light. Why it has to be was another issue we'll get to later on in the course. But speed of light goes at c. It's valiantly trying to catch up to v. Eventually, it will catch up to v, but not yet. This one reaches here first. This one is still heading in that direction. So that leads us to diagram 3.3. Here. And so now Alice, his spaceship, will move it over one more clock here. And so now it's here. See, where was it? 1, 2, 3, 4, 5. I think here is where it is now, that front part. So there's that clock. Here's that. Here's the gun in the middle. Now remember, we'll pretend maybe this is this clock when it was here, it was recorded TB1, but remember what Alice observed when she saw that photon hit that clock. That clock was, and this is on your diagram in the handout, that clock was at TA when it's back here. Okay, because when that photon hits that clock, it triggers a photo and it reads TA for Alice. So let's just emphasize this point before we finish off 3.3. So when Alice reads or observes T sub A on her, call this the rear clock, on her rear clock of her spaceship, Bob sees TB1 on his clocks. Okay? So, just a reminder, so this was actually, I wrote it there, but when this clock was in this position here, photon hit it. Remember, that's what Alice read, T sub A. Now, at this point, this clock has moved on, and we'll get back to that in a minute, but what do we see? And this is no longer TB1, so now we're at diagram 3.3. So Bob's clocks have moved on. Now they're all reading TB2 here, and this is TB2, and this one also is TB2. They all read TB2, whatever time that happens to be. It's just later on than TB1. And now finally he sees this photon hit that clock, and again he would take a little photo right at that instant and says, okay, my clocks all read, not TB1, sorry about that, TB2 at that instant in time. So, what else do we know about that instant in time? Well, we know that Alice, when she takes a photo, when that photon hits that clock, her clock reads T sub A. Because remember from our initial diagram, 3.1, really, or even before that, I should go back to not 3.1, but diagram 1, when, as far as she's concerned, when the light pulses hit her clocks, they both read T sub A. They're both simultaneous, no big deal. Okay? Now Bob is saying, and remember again, Alice is moving this way with velocity v. Now Bob is saying, something's wrong, Alice, because a minute ago, the photon, or a few seconds ago, your leftward-going photon hit this clock and it read T sub A, but my clock read TB1, and the other photon hit this clock. It read TBA, T sub A, but my clock is at TB2. We've got a problem here. Alice thinks that both, according to her clocks, both the light pulse hits were simultaneous. Both her clocks read T sub A at that point. Bob is saying, Alice, you messed up on your synchronization of your clocks, because clearly by my clocks, this first photon hit, light pulse hit back in diagram 3.2 occurred at TB1. The second light pulse hit occurred at TB2. My clocks are synchronized. It's your clocks that are messed up at the point. Meanwhile, Alice is saying, my clocks are perfectly synchronized. I see both the photons, both the light pulses hit at T sub A. They're simultaneous. My clocks are synchronized. It's your clocks, Bob, that are messed up. In other words, you should be reading the same time on your clocks for the light pulse hits, not different times. And all this comes about, the key point here is, when the photons were shot off in either direction, the light pulses, the velocities did not add. This velocity of the spaceship moving to the right did not affect the velocity of the light pulses, unlike regular objects like paintballs, where the velocities would add. Velocity of light in both directions is always c. No matter how Alice is moving, Bob will always see those velocities to be c. Alice will see those velocities to be c, even though intuitively, in our common sense understanding of how velocities work, if something is moving and then you shoot something else out of it, the velocity of the two things are going to add together. Doesn't work that way with light. And here's our first strange result because of that. And this is one of Einstein's key insights to time is suspect, that synchronized clocks, all Bob's clocks are synchronized in his frame of reference. Alice's clocks are synchronized in her frame of reference. Okay? Therefore, if you talk about simultaneous events, Alice is saying the two light pulse hits on her clocks were simultaneous events because they both occurred when the clocks read T sub A. Bob is saying no, they were not simultaneous events because one occurred, the first one over here occurred when my clock read TB1, and the second one over here occurred when my clock read TB2, and I know my clocks are synchronized. So something's wrong here. Well, what is wrong, really, is that simultaneity is relative. An event that is two events that are simultaneous to one observer will not be simultaneous to another observer, especially when you're dealing with the speed of light here. Now, why don't we recognize that in real life? It's because this only comes into play when you get speeds very close to the speed of light. We'll see more of that as we go along here. But that's really the key aspect here of the relativity of simultaneity. Comes from the fact, from Einstein's two postulates, the principle of relativity plus his principle of light constancy led to the insight that the speed of light is going to be the same no matter who's observing it. It's not going to be c plus v or c minus v. Bob will always see the speed of the light pulses as c. Alice will always see them as c. And because of that, simultaneity sort of goes out the window in terms of being an absolute type of thing. You cannot say two events are absolutely simultaneous. They may be simultaneous to Alice, but not to Bob, or they may be simultaneous to Bob, but not to Alice. But it was just this key insight that sort of starts the weirdness in terms of some of the other results of the special theory of relativity. And in fact, later on when we talk about some of the paradoxes of the theory, if somebody gives you a situation and says, well, clearly this shows that the special theory of relativity is incorrect, usually it means that they have not correctly understood the relativity of simultaneity, because this is at the key, the key foundation behind a lot of those weird results. that don't seem like they should be correct. So this is something to ponder, reflect upon, go over these diagrams again, see what's going on, convince yourself that Alice sees the two light pulses hit at exactly the same time. That was our first diagram, I guess 2 video clips ago. And because as far as she's concerned, she's stationary, she's not going anyplace. And yet Bob, observing Alice going along here, observes the light pulses, but still observes, Alice observes them at velocity c, Bob also observes them at velocity c, which means that this light pulse takes longer to reach that clock, which is moving away from it, than this light pulse takes to reach that clock as it's moving toward it. And therefore, that's where you get the differing opinions, really, on whether the two light pulse hits on the clocks were simultaneous or not.